Today we are going to talk about a series of 2 lectures on optimization. You may wonder, why do we want to talk about optimization if it is a machine learning course? If you think about machine learning a little bit further, you realize that it's all about setting up a correct loss function, putting up a proper learning model, and then have the right features, and then what? Well, you need to tune the parameters of your model, and this can only be done when you have a optimization algorithm. Now, if you have any experience in deep learning, you realize that there are built-in optimization toolboxes like Atom Optimizer, things like that, where they're running stochastic gradient descents behind the scene, right? And it is because of all these optimization algorithms that makes machine learning so powerful. So I want you to look at this diagram, which is the like an outline of the first part of our course. We talk about lecture 1 about the model, and then we spend some time in lecture 2 talking about the loss function, regularization functions, and then last lecture we talk about some non-linearity problems by turning the column space perspective into row space perspective. And so now we have everything set up. Then we ask, can we talk about the optimization algorithm? Because this is really one key component of the machine learning pipeline. Now I want to divide the discussion of optimization into 2 lectures. This lecture we want to talk about some basic terminologies, something that you should have seen before, like what do I mean by optimum point? What do I mean by taking gradient equal to 0? Why do we have that kind of notion? I also want to talk about what do I mean by convex functions. It's something will be extremely useful when you study a machine learning algorithm, because convex and non-convex is really the division between easy problem and not easy problems. Okay, we used to think about linear versus nonlinear, but nowadays it's really about convex versus non-convex. So we want to get some basic idea of what is convex, convexity, and then optimality according to convex optimization. Okay, then we also want to talk about a very baby level of constraint minimization, because for most of our course we will be looking at unconstrained minimization, but we also want to know a little bit about constraint minimization so that when the problem comes, you know how to handle that properly. All right. Okay, so that's the plan for today. And then for the next lecture, lecture number 5, we will talk about something that you should have heard, which is gradient descent and stochastic gradient descent. Okay. Now you may come across these terms very often, but what do they really mean? Why is this negative gradient direction the direction that we should use? And what do I mean by stochastic gradient descent? Like why is the stochastic gradient descent so powerful in all these non-convex scenarios? So we want to take a quick tour over there, so now after these 2 lectures, you should have the tools. Even it's a black box tool, you know basically what they are. Okay, so that's the goal of these 2 lectures. And then afterwards, when we go to the other parts of our course, part 2 on classifiers, part 3 on uncertainty principles, things like that, we don't have to worry about these optimization algorithms anymore. Okay, we just know that there is some kind of algorithms that have certain properties, and then I'm going to use them. Is that okay? All right. Now, if you really want to go deep into optimization, there are other courses on campus that are really, really deep into optimization algorithms, which you are encouraged to take a look at those courses. Okay, so here is the outline of today's lecture. As I gave you already some brief introduction, we will talk about unconstrained optimization, and then convexity, and then constraint optimization. Okay, so briefly, 3 parts. Okay. All right. So let's go into the first topic. Is what do I mean by optimization? Well, optimization by itself is a very simple problem. You have a function f(x), and then you want to find a point x in certain set. I call it a x set. I want to find an x in the set such that this function is minimized. It's an extremely general problem that you will encounter basically in all engineering problems. So what do I mean by a minimizer? Well, there are two types of minimizers. One is called the global minimizer, and it says that this X star has to be the lowest possible value than any other values in the set when you evaluate them. So you put an X star into your F, you evaluate this value, it has to be lower than anyone else in your set X. Okay, so that would be called the global minimizer. The alternative is called a local minimizer, meaning that you put a small ball surrounding the X star, and then within that small ball, it is the lowest point. Okay, so that's the definition of a local minimizer. Now, if you want to get a picture, it would be this. So here you have a function. You have multiple local minima. Okay, if you look at the entire range of your X, then this point will be your global minimizer. Now, if you put a small neighborhood around this portion, then you will get a local minimizer. A local minimizer can be a global minimizer, or it may not be the global minimizer. Okay, you can have multiple local minimizers, but usually you will have one global minimizer. But is global minimizers always unique? It's also not true. If it is a global minimizer, then what I mean is that your objective value is minimized. That's all it says. Okay? Now, whether you can have unique X star, that's not guaranteed. Let me give you an example here. Okay? So imagine that you have a function that has this shape, and at the bottom of this function is all flat. See that? It's all flat. Then how many global minimizers are there? Well, you have all the points inside this interval. They are global minimizers because they do minimize the function. The value evaluated at these points, they have the smallest value. So they are the minimizers. And are they global? Yes, they are global because for the entire range, it is the smallest. Are they unique? No, they are not unique because you can find multiple of them. Because it is flat, you have multiple of them. So being a global minimizer does not imply that they are unique global minimizers. When do you get global unique minimizers? You only get that when you have a strictly convex function. Now, what is a strictly convex function? A strictly convex function means that it's a function without any flat region at the bottom. Okay, so that is called a strictly convex function. This is called a convex function, but it's not straight because at the bottom you will have values they share. Okay, that's why people love convex optimization, especially they love strictly convex problems because any local minimum will be a global minimum because it's of this convex shape. If you have another bump here, then this is no longer a convex function. All right, so people love convex function because any local minima is a global minima, and then if it is a strictly convex function, then furthermore you also guarantee that the global minimum is unique. So by solving my training loss function, I can get the best solution ever possible according to your loss function. Okay? So trying to disentangle different terms in your mind. Okay? You may come across these local minima, global minima in different ways. Be very careful that global minima is not unique. That is a very key point here. Okay? Now, when we talk about optimization, of course, we need to characterize the solution. We want to say that, look, I give you a point. Can you tell me whether this point has reached the optimality condition or not? Then we want to examine the optimality conditions. Now, what are the possible optimality conditions? Well, these are the two optimality conditions. The first order condition and second order condition, something that you have learned back in your undergraduate degree when you take your freshman calculus. Okay? The first order condition says that I have a function, I take the derivative, and it has to be 0 when it is a minimum point. Fairly standard. Okay? The second order condition says that my curvature has to be positive. Right? Otherwise, think about this. You have a minimum point, you have a maximum point. These 2 points, you always have the gradient equals to 0. Right? The slope is 0. But which one is the minimum point? Well, it has to be this one. Why? Because you also measure the curvature. So that's why you want to look at the second order condition. So that's the basic, very, very basic level of telling you whether a point is optimal or not. Now, of course, in this course, we're not interested in the freshman calculus version where you only worry about a single variable case. In almost all the machine learning problems that you encounter will be high dimensional spaces. So then we ask, well, how do you ever derive these equations? Okay, can we have a more systematic way of understanding these? So I want to comment on the following pair of conditions. One is called the necessary condition. The other one is called the sufficient condition. Necessary condition says that if X star is a global or local minimizer. Now the difference between local and global is that whether you put a bar around your point or you look at the entire domain. Okay, so X star is a global local minimizer. Then, okay, if this is true, then you will show that the first order condition is satisfied, and then the second order condition is satisfied. Okay, so if you have a global minimizer, then these 2 points has to satisfy these 2 conditions. Now, the reverse is that now I give you a point, you want to check whether it is a global minimizer, then these are not sufficient. Okay, you want to check first, of course, the first order has to be 0, but then the second order condition, you want to make sure that it is strictly greater than 0. Okay, now this notation means what? Well, so the gradient square, it means that a Hessian matrix of a function. Think about it's a high dimensional function, right? So it is a multiple entry going in and then one value going out. So it's like a functional mapping. Okay, so now when you put this in, then calculating the gradient will give you a vector. It's a high dimensional function, right? And then now if you take the second order gradient, that will give a matrix. That's called a Hessian matrix. So by putting this greater than sign here, I mean that the Hessian matrix is strictly positive definite. If I put an equal sign here, I mean that it is called the semi-positive definite. Okay, and the difference is that one here you look at the eigenvalues. The eigenvalues, they are all positive. The eigenvalues of this matrix, they are non-negative. All right. So if you can show that your X star can satisfy both of these 2 conditions, then you can say that your point is a global minimum. Now, the 2 conditions, they are not the same. Okay. The reason that they're not the same is that one says that if you're already a minimizer, then you need to satisfy these 2. Okay. The sufficient condition says that if you satisfy these 2, then you will become a global minimizer. All right, so this is the sufficiency is really for you to check whether a point is minimum or not. All right, so now the following 2 slides, I'm going to show you a few arguments of why these 2, the first order and second order conditions, are necessary to worry about. Okay, how do they come up in the first place? Now, if you read the textbook not on a single variable case, okay, on any high dimensional case, you will see at least 1,000 different versions of explaining this phenomenon. I will just pick the simplest possible explanation here. Okay, so why do you want the first order condition? Okay, so first of all, suppose that your X star is the minimizer. And then what you do is that you pick a point, okay, you pick a point here, X star, and then you pick a direction D. Okay, so let me go to the picture here. Okay, so this is the next slide. So first of all, you start with X star. Okay, and then you pick a direction D. This direction D can be anywhere, okay, in the space. You pick a direction D. Since you note that, okay, this is a small perturbation from your X star, you can do this thing called the Taylor expansion to the first order. Now, I'm lazy, so I'm ignoring the second order and higher order terms. I just remove them. So if you look at the first order expansion, then you get the F evaluated at X star, and the epsilon times the gradient transpose with your search direction. Okay? That's just a very standard thing of doing expansion on the point. Now, you can do a very simple rearrangement of the terms as the following. First, you subtract this term from this f x star, like what I have here, and then divide the epsilon. So you have this ratio. Now, if you look at this ratio, what is it? This ratio says that I am taking the difference between these 2 points. There's a search direction divided by the epsilon, which is a step size. This is like a gradient. Yes, if you take the limit of epsilon going to 0, you indeed get the gradient along that d direction. So that is the gradient. And then the gradient will equal to what? Well, the gradient will equal to this, the gradient of f evaluated at x star and transpose with the d. Okay? Now, since you say that this is the minimum point, this is already the minimum point, then you look at this expression here, it has to be positive. There's no way for it to be negative. So you have this being positive. That means this gradient f transpose d has to be positive for any d that you choose. Now, how can you make this to be positive for any d? The only thing that you can make it happen is that the gradient has to be 0. Right? So now, if you can, right, if you can ever find a f that is non-zero, then I can always find another d that can make it to be smaller than 0. Right? So for this inequality to hold, the only possibility is to make the equality to hold for all the d's. So here is a diagram. So if you are not at the optimum point, you're at x star, you're not at the optimum point yet. Then what you do? Well, you draw the gradient. Okay, draw the gradient. This is the gradient of f evaluated at x star. And then you draw a d. Then you take the inner product, right? Or like what I'm doing in the previous slide. You take the inner product. The inner product has to be negative because, well, this is turning into opposite direction. I can always find a d. If you are not the optimum point, I can always find a d that is opposite to you. Okay? Now, if you are at the optimum point, then I'm sorry, because at optimum point you are 0 anyway. No matter what search direction I pick, it has to be 0. Okay? So now if you ever read the textbook, you may encounter 3 pages or 4 pages of proof of doing this. But once you get this idea, it's that simple. Okay? You draw the diagram, draw the gradient direction, and ask yourself whether this d, this orange line, is parallel to you or is opposite to you. There's only 2 ways. Okay? It's either the angle with respect to you is either smaller than 90 degrees or bigger than 90 degrees. Okay? And if you're not optimum point, I can always find an orange line that is having that has an angle that's greater than 90 degrees. Then that shows that you are not optimum yet. Okay, because along this direction, if I move along this direction, I can reduce your objective value. Okay? So that is a very simple picture explaining the notion of first order optimality. Nothing more than finding the direction d that can make yourself go into the negative gradient. How about the second order condition? The second order condition is named. You need to look at the second order property. And so what I do, well, just to take the same trick as before, you expand this term, but now up to the second order term, and ignore anything that is higher order. Okay, anything beyond 3, ignore them. Okay, so now you have expansion of 3 terms, but the first order term, you can ignore that because it's already proved to be 0. So that will be gone. And then what? Well, and then you sort of do the exact same thing as what we do before. You rearrange the terms, and then you look at this gradient. You look at this directional derivative. And since x star is the minimizer, and so any point that is different from the minimizer will have a higher cost value, and so it has to be positive. No matter what. No matter what d you choose, it has to be positive. If this is positive, on the right-hand side of this equation, you have this equation here. D transpose the Hessian times the d. And then what? Well, this has to hold for any d. How can this be possible? The only thing that can make it happen is that your Hessian has to be positive definite, a positive semi-definite, right? Because here you ask to be, this one has to be greater than 0 for any d. How can this happen? Well, you really want this to be a positive semi-definite. That is the criteria. Okay? So again, you do not need to do a lot of complicated things, but just drawing a diagram, doing a simple analysis of the Taylor expansion, you can get all these first order and second order conditions. Now you ask, how about the things I learned in the freshman calculus? It's the same thing. It just reduce all this expansion to one-dimensional function. It's the same story there. Okay, so why is the second order condition, the necessary condition and the sufficient condition, they are different? Well, it's because if you are a positive definite matrix, meaning that greater than, strictly greater than, you're guaranteed to have a minimum point. But if you have a positive greater than or equal to sign, you can run into a trouble like this. Okay, so you can have a surface where in one side it will be positive curvature, and then the other side you will have a negative curvature, and that's called a saddle point. And in many optimization problems, you do run into this issue of saddle point. Okay, now therefore having the sufficient condition, if I can show that at my X star, the curvature is strictly positive, then I can guarantee that it is this case and not that case. Alright? Okay, so that illustrates a few concepts. Okay, I know I'm like doing a rocket fly of one semester long on optimization in just 20 minutes. But see, what we really need in this optimization, there are only a couple of things. The definition of optimum point, and then the two conditions that you need to check, first order and second order, and a picture to explain the first order and second order.